You read about this one being sneaky. Number 2.
Yeah.
What?
What is it?
Oh,
So, 2 digits,
oh, definitely.
Because you think 2 digits, there's 10 digits.
no 5s.
But there's no 0 in the 10 digit, because that's not.
Yeah, so I said between 10 and 99, so yeah, the first digit is tricky. So, we're not allowed to pick any 5s. So our first digit has to be something 1 through 9, so 1, 2, 3, 4, 6, 7, 8, 9. So there's 8 possibilities for the first digit. And the second digit there's 9 possibilities. So product rule, 72. So there's 72 two-digit numbers containing no 5s. If you want to contain exactly 1 5, you've got 2 possibilities. Either this digit can be a 5 or that digit can be a 5. So if the first digit is a 5, and then this digit can be any of these, 0 through 9, but not including a 5. So we've got 9 options there. So there's 1 way to pick this digit, which is a 5, 9 ways to pick the second digit. So there's 9 ways to construct a number with a 5 in the beginning. If there's not a 5 in the beginning, then there's 8 ways to pick the first digit, and there's 1 way to pick the second digit, which is a 5. So there's 8 ways to do that, and this is a sum rule. We can either do this or this. So there's a total of 17 numbers. How many 2 digits numbers containing exactly 2 5s? 55. Yeah.
So for A and B, if we did it kind of the, I don't want to say obverse way, but if we did the size of the population minus the size of all the numbers with exactly 1 5,
Sure.
is that a valid
That works.
conclusion? Yeah,
2-digit numbers containing either 1 5 or 2 5s. Well, we already found how many contain exactly 1, that's 17. And we know how many contain exactly 2, that's 1, so there's a total of 18. That's a simplified sum rule. And how many 2-digit numbers contain either 0, 1, or 2 5s?
Oh my god.
It's the
okay. Size of the population.
It's just the size of the population, all numbers from 10 to 99. So there's 90 numbers there.
So I totally misread the question, thought it was like asking for a number containing 1, 2, or 5.
Okay,
Oh, yeah.
So
that's harder.
Yeah,
that's what I kind of did.
Okay, that's fine.
I did read that way at first too,
Yeah,
so.
I can see that. No, I can grade it based on how you did it. That's a harder question anyway. So the harder way to do that question is to just add up your answers. So this is the number that contains no 5s, this is the number that contains 1, this is the number that contains 2, 72 plus 18 is 90. So that's your answer for E. But it's also just the whole population. So how many socks do we have to pick out?
6.
6. Why?
Because
5
Fish and
buckets.
Because it's a pigeonhole thing.
Because at worst, you could pull 5 and get 1 of each.
Right.
And then you have to have a pair.
Right. So you can picture after you pull your socks out and go to the well-lit room, you have 5 bins for your red, blue, green, yellow, and black. And you start putting your socks into those bins. And if you only picked out 5 socks, it's possible to have just 1 sock per bin. Of course, they could all end up in the red bin, but it's possible you could have 1 in each. But if you have 6 or more, at least 1 bin is going to have 2 things. That's the pigeonhole principle. And if 1 bin has 2 socks in it, then you've got a matching pair. So for number 3, the answer is 6. What about the octopus?
Use the silly function and
generalized pigeonhole. If you have n objects and m bins, then you're going to have ceiling n divided by m objects in at least one of the bins.
All I did was point out, probably the same concept, honestly, but just that, the worst case scenario is, in this case, 7 items in each bin, and then you tack on 1 to that.
Right.
So that you can generalize, you can just compute the number of objects times how many you need to complete a full set minus 1, plus another 1.
Yeah. And you're really kind of redriving the generalized pigeonhole principle when you do that. You can think of it as saying I'm putting 6 into each bin, and now I want to know how many do I have to pick to additionally put into the bins so that one bin has at least 2 more.
I did that without realizing that's what I was doing.
Yeah, throw your weight your hands and say, by the generalized pigeonhole principle.
Oh, I have a complicated note.
Okay.
I did the combination with repeats
Okay.
allowed. So I got the number of all possible combinations.
Okay.
And then I said, well, if you've got that many, you're guaranteed to get
Right.
any pair. So I guess I didn't realize there's just a
Is that the
pair.
path you were heading down to? With combinatorics?
I considered it first, but I couldn't figure out any way to apply it.
Okay.
So I just went, you know what, I'll plug it all into a spreadsheet and see if any patterns emerge, and sure enough, one did, so
Yeah.
I generalized it.
Cool.
And I really just, I did the same thing he did, but I didn't do a spreadsheet or anything, because it's the same thing where if you consider the worst case, right,
Right.
of it taking forever and you absolutely pick out 35 different socks and they're all,
Right.
you know, and they happen to all wind up with you got 7 of each. You can't get any worse than that,
Right.
And
one
then you just
more
add
and
one
you
more
have
and you have to have an 8, a set 8. Yeah.
Well, I think the worst case scenario would be actually pull out the second sock and it's like magenta or something.
Yeah, right.
Well, yes, that's the real worst case.
So the answer here is then, is it 8 or is it 36?
It's 36.
Okay, that's what I thought.
Yeah, because
I thought you said
35 will let you get 7 in
I
each.
thought you said 8 earlier, I'm like,
No,
how
no.
is it 8?
Yeah, no, 36.
I ended up going to combinatorics and I got 56, so I don't know where I was in that point.
7 times 8.
That is
Sometimes I know.
You had your hand up earlier.
For the pigeonhole, would the number of colors be the object and the bins would be the feet?
So n in this case is what we're looking for.
Looking for
That's the
7.
number we're trying to find.
Oh.
And m is 5, the number of colors.
Okay.
And this is what we want to have be at least 8. So find n such that ceiling n over 5 is 8. So find the minimum n such that that ceiling is equal to 8. And so as long as this is bigger than 7, its ceiling will be 8, so the first n that makes that bigger than 7. So n is bigger than 35.
Because we're saying that it has to be an integer because you can't pull out.
Can't pull out a fraction of a sock.
But you can pull out the limit from the dryer or whatever.
Yeah.
Well, you know how to spin a net.
That's true.
Make your own socks from dryer, but that just sounds like.
Should I show you this?
I like how it starts with Control-Shift-N, just to, you know, it's a good way to start things.
I love the tangents this class gets on.
Yeah, it's topical.
That was awesome.
That was his cohort, his twin brother by
My
the
evil
same
twin,
name.
yeah. My advisor pulled that out during my PhD defense.
Oh, God.
He was like, well, let's begin with looking at some of the candidates' other work.
Is that when you're like heart dropping, you're like,
No, I got him back, actually. All right, other questions? We talked about one the other day. So, recurrence relation, population at time n is just 3. The previous population, initial population equals 25. And so closed form would be 25 times 3 to the n over 2. And that only works for even n. And if you want to do it for all integer n, you can just replace m with n over 2 and come up with a similar formula.
Yeah,
M's the number.
I missed the N over 2.
Did I miss the n over?
I
What?
got the N, no, I'm
Okay.
complaining about myself.
Yeah.
yeah, I did it generationally, so
Yeah,
it's
yeah.
for each generation.
Yeah,
I got the it increases by 2 bit, I just forgot to throw an N over 2 in there.
Yeah, so if you do it by generation.
Over 2 part. And next one's P of 2. What? Oh, I see. I didn't even realize you could do it that way, but that makes sense.
Yeah.
But we'll say I did it that way.
For the recurrence relation, would it have been just as proper to say Pn plus 2 is Pn?
Yep, same thing.
And then for the closed form, so if it was an odd hour, would that still work?
We normally define these things for integers. And so if you think of it as generational, odd hours would say, what is it like halfway between this generation and next? And we could find a formula for that if we assume something about its growth rate. But we're actually defining a sequence of values. And this is an equation for the nth term of the sequence. So, yeah.
I think on this one I did something where instead of going back 1, I did go back 2.
Mhm.
So I set 0 and 1 as predefined,
Okay,
and that seems to have worked.
okay.
Also, I doubled it instead of tripled it.
Okay, yeah, that everything's always double. Triple's like artificial, but make it tricky.
I think I had a misunderstanding about, could you explain what you mean when you say a closed form?
Just an equation.
Okay,
So this is a recurrence relation. We can't just say, okay, I want to find what P of 8 is, because we need to know what P of 6 is.
okay,
And we can work our way back. We can find P of 6 from 4, 4 from 2, 2 from 0, and we know what 0 is. That's what makes it a recurrence relation.
okay.
We only get the answer in terms of earlier forms. Whereas this, we can just say, okay, n equals 10, this is 25 times 3 to the 5th.
Okay.
So I don't know if closed form is the term the book uses, but it's a formula you can plug in.
So what's your strategy for going to the closed form from the recurrence relation?
There's a couple of ways to do it. One is to start writing out P of 0 equals 25. Let's go with the generations because I like those better. So P of 0 equals 25. P of 1 equals 3 times P of 0 equals 3 times 25. P of 2 equals 3 times P of 1 equals 3 times 3 times P of 0 equals 3 times 3 times 25 equals 3 squared times 25. And if you do this enough,
I got you.
just keep plugging into the recurrence relation, you start to see the pattern.
That's funny because that's actually what I did to come up with the recurrence relation.
Yeah.
And it's like, oh, this didn't take that extra step, but I got you. All right. All
right, so let's go back to trees. And let's talk about what we actually use trees for.
Decoration,
Do it.
oxygen, a lot of things.
Yeah. And photosynthesis. So we're going to talk about what's called a binary search tree. It's a binary tree, each node has 0, 1, or 2 children. But it has this additional property for any given node. All nodes in the left subtree are, and I'm going to say less than a given node. We could say less than or equal to, but I'm going to keep it simple. And all nodes in the right subtree are greater than. So our nodes are going to have values associated with them that are somehow can be ordered, and we'll pick mostly on integers. And so here's an example of a binary search tree. And for any node, if we look at the left subtree, all of those values are less than that given node, and everything in the right subtree is bigger. And this holds everywhere throughout the tree. If we pick this node 15, the left subtree has 13, that's smaller. The right has 18, 20, 24, those are all bigger. So this is an example of a binary search tree. And this is a really useful way to store information. It's going to let us sort, it's going to let us search, and it's going to let us insert new information very efficiently. So let's talk about search first. You've got this tree and you want to know whether some given node is in here. So we want to know if there's a 20 in this tree. Okay, here's what we can do. Start with the root. Is 20 bigger than 10?
Yeah.
So if 20 is in this tree, it's got to be in the right subtree. So now search this subtree for a 20. Start at the root, it's 15. Is 20 bigger than 15? Yep, so if it's going to be in this subtree, it's got to be in this right subtree. So start at the root, there's our 20. If we were looking for 19, it's bigger than 10, so it's somewhere over here. It's bigger than 15, so it's somewhere over here. 19 is less than 20, so it would be somewhere in this small subtree. It's bigger than 18, so it would have to be in the right subtree, but the right subtree doesn't exist, so we know there's no 19. So start at the root, and start, if the root matches the number you're looking for, you're done, you found it. Otherwise, you can reduce your search to either left or right subtree.
So could you modify the high-low game to create a subtree?
This is the high-low game, right? That's basically what you're doing here. And you can think of playing high-low, you could describe that with a tree like this.
Alright.
You have to build the tree though, wouldn't you?
Yeah.
What is there an easy way to generate the tree? Or
It's all easy.
is there a relatively easy way?
Yeah. Building binary trees in C is pretty straightforward. In Java, it's really, really easy because there's all sorts of classes that already support this.
You just use like a linked list or something? Or?
A tree and a linked list are really close to each other. And we'll see exactly what that
So
is.
instead of having a next element structure would be left or right or something like that.
Yeah, it's a linked list where we can actually play high-low. So we start at the middle of the linked list, and we have, instead of a pointer to the next node, we have a pointer to the middle of the right list and the left list. So you can get to the middle of each of those ranges. And each node has a pointer to the middle of the right and the left. And if you take that and you fold it down, it looks like this.
So, what are trees generally used for in the field?
Everything.
Older tree.
So they're used for storing information that you want to search quickly. They can be used for sorting information, we'll get to that in a few minutes. And they can be used for recursion. When you do a recursive function, there's a tree-like structure taking place, being built de facto in the background to remember all of your calls and where you need to go back to and where you were. That can all be expressed as a tree-like structure. When you're browsing the web and you click on a link and it takes you to a new page, and you go a few sentences down and you click on another link and go to a new page, you can hit the back button and come back to where you were. That can be all organized as a big tree. In fact, the whole web can be viewed as a tree in some sense. Computer networks have a tree-like structure, but they're not binary. Neither are web pages.
A tree defines that it's not a loop.
Yeah.
But
And you can have loops on web pages,
Yeah.
but the general structure of having a parent and a child and being able to descend down and come back and go down another path is very tree-like.
So, because it looks like you can't have the same number in one tree twice.
Yeah, in this, and I could say less than or equal to, and then we could have multiple numbers.
What if you had both of them less than or equal to, greater than or equal to?
Then it would be equal. So, yeah, I would say if it's less than or equal to, put it in the left, and if it's greater, put it into the right. I think that would work.
Alright.
And this, we can still think of as kind of abstract, right? We don't usually just have a tree of integers. We would have a tree of, I don't know, linked lists, arrays, pointers to files, other trees. You can have forests, things like that. But for looking at the basic functions and behaviors and uses of trees, we can just think about integers. And so I'm going to make it easy on myself. Put the integers in once. Yeah.
So if that was a tree of arrays, would you just have some integer-like value that you would be checking against to do a search, or?
If you're going to do a binary search tree, you need to have these things well ordered. There needs to be a way to take any two of them and say this is greater or this is less or this is equal. So if you were doing strings, you could do it lexigraphically, right? Just sort by ASCII codes. If you're doing arrays, I'm not sure what you'd be doing, but maybe it would be arrays indexed by phone number or something, and your phone numbers are well ordered. But you have an array of phone calls that have been made to or from that number. Stuff like that. And that's all we're gonna like go totally geeking out on in 222. Is like all the depths of this kind of stuff. So we'll have fun with that. All right, so we can do searches really efficiently. How efficient is this?
Log. 2 operations to find 20.
2 operations to find 20, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers in here. So if it was a totally unordered array of 10 numbers, it might take me 10 operations to find the last number or to decide my number's not in.
Might take you just one.
It might take me just one. If it's a sorted array, I can play high-low. Right, I can start in the middle of the array, and if my number's bigger than that, then I can search in that second half of the array, and so on. So I play high-low with the index of the answer, basically. With this, what's the most number of searches we're going to have to make?
4?
The height,
Yeah.
right? It's the height of the tree.
I can't remember.
So yeah, in this case, it's 3, I guess. But in general, it's the height. And remember, we talked about balancing a tree. A well-balanced tree is short and wide, right? A short tree, a tree with a low height, means it's not going to take a lot of operations to search it. So a well-balanced tree with 1,023 nodes has a height of 10, or maybe 9, I'm always off by 1. But 1,000 numbers, 10 operations to search. Okay, so yeah, it is log n. And that's very efficient. 1,000,000 numbers, 20 operations. 1 billion numbers, 30 operations, as opposed to 1 billion operations.
That's pretty good.
So that's a pretty good improvement. So log n is our friend. So yeah, height of the tree controls the amount of work we have to do. All right, so we can do searches like this. What if we want to add something to this tree? What if we want to add the number 14?
You do it like a search.
You do it like a search. It's bigger than 10, so I've got to add 14 over here. It's less than 15, so I've got to add 14 to this subtree. It's bigger than 13, so I've got to insert it into this right subtree. While there is no right subtree, so I can make a right subtree that's just got 14. And it's still a binary search tree. Because of the way I inserted it, it still follows this property.
So, entering is the same log operation of log n.
Yep. Which is better than an array. Because if we have a sorted array, and I want to insert a number that's smaller than any of my numbers, I've got to shift everything down 1. So that's potentially going to take n operations. With this, it's going to take log n operations.
Yeah, except if you have to add 16.
If I want to add 16,
It goes after 14.
it's going to go to the right of this, to the left of this, to the left of this. It's going to come out there.
Now it's
So
not
that's going to
balanced
increase the
anymore.
height.
Yeah, now it's not balanced anymore.
Yeah.
So, how many operations does it take to remove a node?
Removing a node is trickier.
Much trickier. What if you want to remove 15?
What if you want to remove 10?
Oh, we killed the
Get rid of
tree.
it,
We
sort
killed
it,
the tree.
get rid of it and sort it again?
You could get rid of it and start it again, but
Doesn't sound very fast to me.
no. But it's not too bad. So when we added 16, we increased the depth, and we've still got a pretty short length over here, and we've got a long path over here. So usually what we're doing is when we're trying to worry about efficiency, we insert things. Sometimes our tree gets unbalanced. And there are ways to rebalance it. It actually takes 3 operations to rebalance if it was balanced before you inserted this next node. We'll do that in 222 also. It's called an AVL tree. If you don't keep it balanced, though, if you insert 100 nodes and then say, hey, it's unbalanced, it can take a lot of work to rebalance it. But if you insert 1 node and now it's unbalanced, you can do 3 operations, get it back to balance. And that also works for deleting. You can delete a node and you can go boom, 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 get it balanced again.
So you'd be best off inserting or deleting and then rebalancing and then inserting and doing that.
Yeah, you
over and
rebalance
over.
every time that you
Every time.
insert or delete.
If you don't worry about rebalancing, removing like a 10 wouldn't be that hard. 'Cause you can just take the minimum of the left subtree or the maximum, or no, wait, no, the maximum of the left subtree or the minimum of the right subtree and replace it there.
Awesome. So yeah, we could remove the 10 and we could put the 9 up here. And then it's still a binary search tree. Or we could remove the 10 and
13.
put the 13 up here, and then we've got to remove the 13 from this tree. So we could put the 14 up there. So it takes a few steps, but it's not too bad. And trees are just one of the structures we're going to study, right? All of 222 is looking at all these different structures, and there's different versions of trees, and there's different approaches to maintaining these things. So we'll study something called a heap, which is really efficient for pulling things out in order, really quick to add things and remove things. And these are data structures that are all over most parts of a computer, including all over the operating system. These things are used. All right, so we can search efficiently, we can worry about balance, but we won't worry about that for a few months. But depending on the order in which your numbers come in and you build your tree, if your numbers come in that order, well, here's 1, that's the root. Where's 2 go? It goes to the right. Where's 3 go? Goes to the right, goes to the right, goes to the right. Where does 4 go? Right, right, right. And you're getting a very untree-like tree.
You're getting a stick.
You're getting a stick. And when you search for the number 8, you're going to have to go 1, 2, 3, 4, 5, 6, 7, 8 comparisons, right? That's like the most unbalanced tree that you can imagine. And so, that's okay.
So would it be more efficient to try and pick a number in the middle for the root? In this case, that's at 5.
Yeah, this is actually one of these cases where if you randomize the incoming data, it might end up working better. Or if you knew that there was a number in the middle ahead of time, you could pick a 5, and then this would come out a little better. But even that would come out fairly unpleasant. Because here would be your 5, 1, 2, 3, 4, 6, 7, 8.
Hey, that's still better.
Better.
I feel like any order you could choose other than the straight up input is going to be better.
Yeah. If it's sorted to begin with, this is not a good strategy.
So we kind of want them to be unsorted and
Yeah.
unordered.
We'll actually study some sort algorithms later on next term that some of them actually randomize the data when it first comes in because it's so horrible if the data is close to sorted. It just kills the performance. So you just randomize it quickly before you start building your structure.
It's so counterintuitive.
Yeah, I know. But there's something beautiful about that.
We need to mess up the room to clean it.
Yeah, yeah. Well, that's true, right?
True.
I mean,
Yeah,
that's
that
why
is
it's
true.
so fun, like, doing, like, demolition and starting from scratch. All right, so we have a binary search tree. We know we can search for things inside it. What if we just wanted to see the data sorted? We just wanted to pull out the smallest to largest number in that order.
You go right till you get to the lowest level, then work your way up till you reach the root.
Yeah,
Or,
that gets
no.
confusing.
No.
It's actually left.
Oh, no, that's right, that's right.
Yeah, that's what I meant, sorry.
Yeah.
Yeah, you have to find the
Left,
lowest
right, or
number.
hard, come on.
But yeah, the smallest number in this tree, we're going to start from the root. The smallest one's got to be in the left. It's got to be in the left. It's got to be in the left. There's no left child. This is the smallest number. Yeah.
But you're going to start at 6, then you're going to go up to 7, then you're going to go back down to 8 and 9,
Right.
then you're going to go back up again.
Yes.
So you go left all the way.
Go left all the way.
You go parents and then go right.
Go parent and then go right. But suppose there's an 8.5 here. When you come down here, you got to do it again. Go left all the way, then
But
come to
that's-
parent,
that's
then
not-
go
that's
right.
not less.
Yeah.
8.5 is not less than 8.
7.5.
Oh.
Follow your own rules.
So that
Yeah.
changed things.
So go all the way to the left. Print that node out. So go like left as many times as you have to. And then print out the node at the parent. And then go to the right and repeat the process.
Go all the way down.
Go all the way down to the left. There's your 7.5. Then print out the root node, that's 8. And then go to the right and repeat the process. Well, there's just a single node there. So there's our 9. What do we do after that?
Go to the parent.
Go to the parent. What we just did was we traversed this subtree on the left. Now we print out the parent node. And now we do the same thing on this tree.
Seems like a lot of recursive function.
It is a recursive.
This is a recursive function.
Where you have to keep track of the height of each branch minus one on the next
Mhm.
go right.
Programming assignment. Please say no.
Let's see.
So the process we're talking about is called traversal. Okay, traversal means visiting every node in your tree. And this particular style of traversal is called LNR, left node right. And we can describe it recursively. Traverse the left subtree, and then visit the root node, and then traverse the right subtree. How do we traverse the left subtree? Traverse its left subtree, visit its parent node, and then traverse its right subtree. And we keep doing that.
You said this is left node right?
This is left node right. So traversing this tree, LNR, first we'll do the 6, then the 7, then we'll traverse this, which means first go to the left, 7.5, 8, 9. That completes the first L that we were trying to do. And then we do the root node, 10, and then traverse this. To traverse this is the R we're doing. First we traverse the left subtree, that's 13, 14. To do that, first we visit the left subtree, which is empty, then the node 13, and then the right. That's traversal of this tree's left subtree. Then we visit the node 15, then we traverse this. And we keep going. You'll run out of fingers really quickly trying to keep track of where you came from and where you go back to. Okay, computers are good at this.
That's what I was gonna say, it's fortunate computers don't use fingers.
Yes. All right, let me show you some pseudocode for doing this. So let's say traverse tree. If our tree is empty, there's nothing to do. We'll just return and say I'm done. Otherwise, traverse the left child of the tree. Print the root of the tree. And traverse the right child of the tree. That's your whole algorithm. And you should look at this with some suspicion. As in, where are we actually doing any real work?
Well,
The print the tree root.
yeah, print tree
Because
root.
That's our only print statement.
Because when you traverse to like the left of the 7, so 6,
Mm-hmm.
and you try to traverse to left, there's nothing. So you
Yeah.
print 6, and then you try to traverse right, there's nothing.
Yeah.
So that's the only time that you're actually, the only time that you're really doing work is when you find nothing.
Yeah.
more or less.
So instead of you printing the root, which is 10, you're printing the parent of the node you're at.
So when I say traverse tree left, this is just a pseudocode way of saying if our original tree was this whole thing, this is what tree.left is. And this is tree.right, and this is tree.root. So the first thing I do is I traverse this. And when I come into traverse and this is my tree, the first thing I'll do is traverse this. And when I call traverse and this is my tree, the first thing I'll do is traverse this empty left child. And when I try to traverse an empty tree, it'll say the tree is empty, nothing to do. And then I'll come and I'll say print the root of this tree, which is a 6. And then I'll traverse the right subtree, which is empty, it'll say there's nothing to do. And then I'll return from my call that said traverse this. that was the left, and then I'll print out the root, which is 7, and then I'll traverse this subtree. And it's almost embarrassing, right? It's doing all the work for us. It's keeping track of everything. It knows where to go back to. And we're just kind of like saying, okay, just traverse the subtrees and print the node in the middle.
And it's funny that someone got their PhD by just adding, like, figuring out the search function on a binary tree.
Yeah.
I mean, the binary tree was only made, he just was like, oh, hey, if you sort it like this, you can search it.
Yeah. There was a lot of good stuff in the 50s when this stuff was developed, and these people were mostly mathematicians, and it's just like crazy. When we talk about graphs, we'll talk about Dijkstra's algorithm. Dijkstra did a lot of work on graphs and finding shortest paths. When he went to get married, he had to, apply for his marriage license, and under occupation, he put computer scientist, and they're like, that's not a real job. So he had to change it to mathematician to get his marriage license. Because there weren't computer scientists in the 50s and 60s, I guess.
The important thing about this, about the tree, is just remember every time you say traverse, it means you're switching the root to the next node.
Yes. Right, and this is the magic of recursion, right? When we say traverse, we're recalling this, we're freezing what we were doing, and we're starting a whole new execution of this traverse code with a different tree. And when that's finished and it finally returns, and this is the only time it'll return, then we're right back here and we go ahead and we do this statement, and then we traverse the right.
Is traverse a class in Java? Because that really looks like Java code right there with the tree.
Yeah, I wrote it in object-oriented style with tree.left. It's a method that we would write in a tree class in Java, yes. And we will.
Can you make a struct that contains itself?
Yes, absolutely.
Okay, so that's how
and we
this
will.
stuff works.
Yeah. So a tree will be a struct that contains a left tree, a node, and a right tree, basically. But they'll be pointers. I didn't say the pointer word. Yeah, so the definition of these structures will be recursive in some sense also. So how do we search for something in a tree?
That depends on how it's organized.
Binary search tree.
I mean, okay, I guess, is this just how it's done? You put the smaller stuff on the left and the bigger
Yeah,
stuff on the right?
that's a standard binary search tree.
Oh, okay. Well, like you said earlier, if we wanted to find 20 or something, we'd use the root node, we'd see if it's bigger or smaller, and then we'd go that direction.
Mm-hmm.
Well,
Pretty much going to be the same as traverse, but we're just going to have the traverse statements and if statements, seeing if it's high, traverse left, low, traverse
Mm-hmm.
or low, traverse left, and high, traverse right.
So we could do this recursively.
why do we need to do it recursively? We're not
Because
going to
it's
come
fun.
back to the top.
Because it's actually the only way.
So if the root's equal to our data, then we just return true. We found our data.
Otherwise.
If tree is null, return false.
Data.
If there's nothing in the tree, we're not going to find our data in there. So if it's null, return false. If the root is equal to the data, it's true. Otherwise, search the left tree, and if we find the data in there, return true. Otherwise, search tree.right, and if we find it in there, return true. Otherwise, return false.
Can you just make a flag burst equal to like 0, and while it's less than that, go to left?
Yes, we can do this without recursion. We can start here and we can move through the tree, but you got to keep track of pointers and all sorts of things like that. And, but we can also do it recursively.
But why do we have to search both subtrees if we can just compare our data to the
Well,
node of
you
our
could.
tree and then just choose?
Yeah, so we could say if it's less than the root, search the left subtree. If it's bigger than the root, search the right subtree. But if you don't even like if statements with numbers, you can just search them both. So yeah, lots of different ways to do this. But the essential point is we're using the search routine to write the search routine. Right, so yeah, it's a better way to compare your data and then just search left or right. But again, you're doing almost no work, right? You're just saying, okay, I'm going to turn this into a smaller problem. And how do you solve the smaller problem with the thing that you're writing?
So would it actually be more efficient to have it where it's checking if it's low or high, or would it be more efficient just to check
Yes.
both sides?
Yes, definitely.
Definitely more efficient to just check one subtree.
Yeah, remember that the recursives are generally less efficient but easier to write.
Yeah.
Yeah.
So if you can only go down one branch instead of the other, you'll save yourself a lot of work. And this is not too inefficient, again, because the depth of the recursion, the number of times you're going to call yourself, is related to the height of the tree.
Yeah.
So it's not too bad. It's not like Fibonacci numbers that will run for a really, really, really long time. All right, good enough here because we're out of time. We'll talk a little more about this on Thursday. We'll talk about different versions of traversing trees. We'll take a look at some of these things, and we'll start to look at how recursion can be expressed with a tree and how we can sort of track what a recursive function is doing. And then we'll move on to graphs. Wait. Not in here, no.
Oh, I thought there was.
Oh, is there a quiz?
No.
Oh, there is a quiz. Thank you.
Danny, you ruined it for us all.
Yeah. Yeah, no, I wanted a quiz on induction and stuff.
No, why did I?
I would have noticed, and then I'd like
please.
send out an email. So it's not your fault. Yeah, so I'll have a small quiz Friday.
Well, better run away before it gets hurt.
All right, you too.
So is it gonna be Friday or?
Quiz Friday?
Quiz Friday.
There wasn't, now there is.